Okay, well, good morning or good afternoon, everybody, and welcome to this webinar on new technologies in Precast. The screen is paused as we're just getting set up here. Just do this. Okay, hopefully everybody can hear me okay. As Kathy, oh, you must be able to hear because you're putting in the names of the people that are in attendance, so that's great. Okay, we'll get right into it. And this is kind of an exciting, not that all webinars aren't exciting, but this one I was particularly excited about doing because I love talking about new technologies. I love reading about it. I love just geeking out on it. So it's, oops, I'll bring that over here. It's great to be able to talk about it with others that are hopefully similar, have similar interests. You must have those similar interests or you wouldn't be here. So, all right, we'll talk about a wide variety of new technologies, and this doesn't even capture all of it, but these are ones I selected based on my familiarity with it and just how it could impact potentially the precast industry. We're going to start with nanotechnology. We'll talk about embedded technology, a little bit on polymers, carbon capture, 3D printing, and then if we have a little time at the end, we'll talk about some additional areas of evolving technology. Concrete is always evolving ever since from its initial inception thousands and thousands of years ago. This is a sample of Roman concrete, and this concrete was made with some volcanic rock, some brick, and then volcanic ash mixed with limestone and created this concrete that not only worked well for its time, but still works well today. And scientists have actually been studying this concrete because what's amazing about it is that a lot of it has been exposed to seawater. And even with the exposure to seawater, the concrete has lasted over 2,000 years. Whereas if we exposed our concrete we made today to seawater, I don't think we'd get nearly that far if you get to 50 years or 100 years. So how is this concrete different? And some researchers at Berkeley looked at it under different levels of magnification and studied the concrete, and we're surprised to find that within the pore structure of this concrete, they discovered high concentrations of certain minerals like zeolite, phillipsite, tobermarite, and occupying the porous spaces in the concrete. And this was created by the dissolution of some of the materials, including the seawater. So the seawater reacted with some of the materials in this concrete to fill some of that additional pore space. And you'll see that we'll talk about today some of the new technologies is kind of focused on that, like how can we alter concrete, specifically when it comes to pore space, to make it a higher quality, more durable material than it already is. So as far as the Roman concrete, they're actually studying on how we could recreate this, and they haven't come up with the exact formula, but they're still looking at it. So I thought that was interesting. Let's talk about nanotechnology. So when we were talking about that concrete, we talked about how they were examining it on a high magnification. So nanotechnology is technology that is based on a very, very small scale, okay? And it's used in a lot of different industries, including medical, foods that we eat, energy, electronics, of course, as you can see that's readily evident in even the phones that we use, right? Because you remember they used to be, if you're old enough to remember the first cell phones where it looked like you were calling in artillery. Now you've got these little tiny phones, that fit in your pocket. That's all due to the fact that we've been able to manufacture on a smaller scale the same components. And then, of course, its use also in concrete. So nano, what's that mean? Well, it's 1 billionth. Okay, the term nano means 1 billionth. And a nanometer is actually 1 billionth of a meter, okay? So this gives you an idea. Here's some nanofibers compared to a single human hair. just to give you an idea of scale. There are 25,400,000 nanometers in 1 inch. A sheet of paper is about 100,000 nanometers thick, and a fingernail grows about 1 nanometer per second. So you get it, right? It's a small scale. And believe it or not, that's not the smallest scale. There's also a picometer, which is another thousandth of a nano. But we won't get into pico technology today. But nanotechnology, it's basically the use of materials or the study on a level, an atomic, molecular, or supramolecular scale, looking at materials in order to modify them and create new technology, either from a top-down or a bottom-up approach. And where this applies to concrete, well, first of all, we'll go back to our lessons on concrete hydration. Now, what happens during concrete hydration? Well, you have components in the cement, right? And when they mix with water, then it forms new components. So remember, we talked about the tricalcium silicate, dicalcium silicate, tricalcium aluminate. This all rings a bell. So if we just look at tricalcium silicate and we add that to water, well, then that produces calcium silicate hydrate, which is the strongest part of our concrete. It's the stuff that holds everything together, and it's mostly responsible for the strength and the durability of our concrete. And then a byproduct called calcium hydroxide, the CH, which is not as beneficial to concrete. It participates in some of the durability mechanisms, some of the attack mechanisms that affect durability, rather. And so the less CH we have and the more CSH we have, typically would mean it's a better, higher quality concrete. Well, people have been looking at this on a very, very small scale. And what we get is we're able to look at concrete structure on a very small scale, all the way down to those CSH, the CSH and the CH and the formation and the water that gets trapped in between. So if you look at the scale, we look at 10 millimeter scale. That's going to be your biggest air bubbles that you can see with with the naked eye. And then as we get to smaller and smaller in trained air, then we get to, these are microns, micrometers or microns, 1 micron, and then we get to 0.001 micron, which is 1 nanometer. And that, when we get to pores that are that size, they exist in concrete and typically encapsulate water. So some of the water that you use, the water you'll use today in your concrete, some of that water is going to get trapped in these very, very small pores, nanometer scale pores, and they'll get trapped there forever. They're not going to be available to use for hydration. And this creates these gel pores, these very small pores, that does affect, to a certain point, the durability and strength of the concrete. Unfortunately, there's not much we can do about that, okay, because it's on such a small scale. And just to give you an idea of scale here, from this point to this point, the difference in scale is the same as if this was an orange and this was the planet Earth, okay? So that gives you an idea of the pore disparity, the pore diameter disparity between the smallest pores in concrete and the largest pores. So we're talking really, really small. So if we're looking at concrete on a very small scale, like we see here, now this is where we're using scanning electron microscope or some of this new technology that we're able to examine concrete on a very small scale. Now we're able to see, well, this is CSH here, the calcium silicate hydrate formation. That's CH. The CH is typically formed like in platelets. So the calcium hydroxide, there's some CSH growing on the CH platelet. And then those rods that we see there are etranite, which tend to form earlier on in the concrete and then break apart as the concrete continues to mix and cure. And then everything in between, you see these large voids here, those are voids. And some of that will get filled up as hydration continues, but not nearly as much as we'd like. And up till now, like I said, we haven't had the ability or the technology to really understand the magnitude and the effect of those pores until recently. And so what it's enabled us to do is to observe the structure and then develop ways to change that structure on a nanoscale. And that proves to be very, very beneficial. Okay. And this is, we've been able to use advanced levels of magnification, like with nuclear magnetic resonance spectroscopy, to get these kind of photos and be able to study it. And then, as a result, develop technologies like nanoparticles. So nanoparticles, some of the nanoparticles that have been developed or are being developed are nanosilica, nanotitanium dioxide, nanocalcium carbonate, and nanosized cement. I'll talk about each of these just briefly, but nanosilica, which is probably the most widely used nano material, is actually, it can come in two forms. It can come in a powder form, or it can come as a colloidal silica, which is most common, and that's usually in a liquid, so it's kind of added like an admixture. But the nanosilica, what it does, basically it does three things. Now you notice the word silica, right? And so you're familiar with when we say calcium silicate hydrate, there's silicate in the concrete, in the cement, so it's already in there. And we do use silica fume from time to time. And what does silica fume do for us? For those of you that have used silica fume, you've noticed that it does tend to speed up set. It does densify the concrete. It does make it more durable and stronger. Well, the nanosilica used in a colloidal form will actually react and create a denser matrix by doing three things, basically. It has a filler effect, right? Where it, much like fly ash or slag, where it reacts with the CH to create more CHH, right? So it reacts with the not as good stuff, right? Gets rid of it, and then creates more of the good stuff, which is always good. And this was what fly ash does, and slag, and other pozzolans and hydraulic SCMs. But it also has a nucleation effect. And nucleation effect is pretty common among all nanoparticles and other materials, which is it provides a site for hydration to occur. It provides sometimes what they call seeding, where it provides an area for the cement grain as it hydrates to attach to, and the calcium silicate hydrate forms from that point, that seeding or that nucleation site. The more of those you have, the faster the hydration occurs and the more filling of the open pores that you have. So the nucleation effect is the second thing that nanosilica does. And then the third thing that it does is it has the it has a pozzolanic effect and has a filler effect where it actually just by itself. So this is what I meant. This is the pozzolanic effect that we have up here, where it takes and it reacts with the CH to create more CSH, but it also acts as a filler where it just ends up filling additional space in the concrete. So it behaves as a nanofiller between the gel products of calcium silicate hydrate, and it ends up increasing that packing density. Okay, so once again, to clarify, it acts like a pozzolan, right? It acts like a pozzolan. 1, 2, it has a filler effect where it just naturally fills the areas between the CSH gel, and then has the nucleation effect as well that helps foster further hydration. So just those three things makes it an excellent product in terms of it creates a concrete that is denser, has less pores, therefore has higher strength and more durable. Also included in nanoparticles, we have nanotitanium dioxide. Now, titanium dioxide is it's a photocatalytic material that by itself possesses like self-cleaning and self-disinfecting properties. Okay, it's used It's used in a variety of products, including sunscreen, by the way. So it works very well in sunscreen. And it also is used in concrete as titanium dioxide and nano titanium dioxide, where in some concretes, by using this product, it has created what they call self-cleaning concrete, if you've heard that term. Now, how does it self-clean? Well, it has photocatalysts that react with pollutants in the atmosphere, breaks them down, and ends up cleaning the air that it comes into contact with. Now, this is the Jubilee Church that you're seeing down here in the right corner in Rome. And the architect on this is Richard Meyer. And Richard Meyer, his buildings are always bright white. He likes bright white structures. So initially, the intent was just to be able to keep those precast panels. Those are precast panels, by the way. To keep those precast panels bright white. And so they used this titanium dioxide cement so that it breaks down the pollutants that come into contact with it, keeping it cleaner. But now they're further using and developing this titanium dioxide to also, the claims are that it could clean the air in cities and on highways where it's used. And so using it on a nanoscale also has been reported to help improve strength, mainly by virtue of it being a nucleation site, very similar to what we talked about, the nanosilica. Now, this was in Rome. This is actually a structure at the I-35 bridge in Minneapolis. And this was put up after the original I-35 bridge had collapsed back in 2007. They built the new bridge in 2008. These are precast. And this monument is also made with titanium dioxide to keep it white and to clean the pollutants that come into contact with it. Also, there's nanocalcium carbonate, which tends to be more of, it also helps, accelerate the reaction of the tricalcium silicate, helps to accelerate those. So it acts more like an accelerator in terms of its effect, but also helps in strengthening and making a stronger concrete, but not as much as the nanosilica. And then also nanoparticle cement or nano-size cement, also very often referred to as nano concrete. Okay, so if you talk about cement, I'm running out of space here. Okay. There. If we talk about we talk about cement particles are typically in the range of 1 to 50 nanometers, and they can be, depending on the blade fineness, depending on what type of cement you're using. Nano concrete means that you're using something that is smaller, that in the range of 0.5 or smaller nanometers. So it's basically ground to a finer size. And just like the type 3, which is a finer, smaller particle than type 1, it leads to a faster set, higher strength. But when you get to the nano size, they have found that they've been able to create some concretes, and this is still being tested, but they've been able to do some lab tests where they found that they can get relatively the same strength or higher strength using even less cement. So overall, using less cement than you would if you were using typical Portland cement. So not only does it help you achieve the faster set, higher strength, but even if you get the same strength, if you're using less cement, that's both an economic advantage and also a sustainable advantage. Another thing that has evolved is the use of carbon nanotubes. So nanotubes are, it's kind of a form of biomimicry where they looked at spider webs and how strong some of these spider web, the silk that is used, how strong it is, very, very strong. And to try to imitate that by creating these nanotubes that are either embedded within polyvinyl alcohol fibers, PVA fibers, or used on its own as a carbon nanofiber and mixed into the concrete to help control the propagation of cracks on a nanoscale, on a very, very small scale, which overall contributes to the overall strength of the concrete. So this is also something that's out there. They're commonly referred to as CNT if we're talking about carbon nanotubes, and it can help with also providing nucleation sites, which is a common thing, and gives good high strength, enhanced performance, and is really proving to be a promising, continuing, evolving technology in terms of providing a durable concrete. So what are the potential impacts overall of nanotechnology, which I just barely touched? But if we look at what we've just talked about, there are things like faster set, but overall, the biggest impacts are the enhanced durability, the enhanced strength that we may get with these mostly admixture-based technologies, or some of these technologies are embedded within polymers or fibers, and the added durability, the added strength, and also the potential lower environmental impacts associated with any reduction in cement use. Because as you may know, the carbon footprint, or the carbon impact of our products is mostly dictated by the cement, because the cement manufacturing is very intensive in terms of its carbon footprint. And so that in itself is what we're working against as we continue to strive to lower that impact by using responsible methods of manufacturing, things like that. And then the durability of precast concrete, as opposed to other materials, helps negate that initial very large impact. But if we can use less cement by using an SCM or by using one of these materials, obviously that helps add to the sustainability of our products. Okay, moving on to embedded technologies. So this is an actual photo of a OmniVision camera, an ultra compact sensor that was designed specifically for medical applications, like in endoscopes or catheters. It can be designed for a wide range of applications: dental, veterinary, industrial, wearable, and forensic devices. But this is currently the world record holder for the smallest device ever made by man. So you can see that that's very small. And these types of sensors or small devices have been used quite a bit in electronics mainly, but also, like I said, in medical, in consumer goods, and also concrete. And that's what we're going to talk about. Let's start with that I-35 bridge. Remember we talked about that earlier, where that monument was built. This is the new bridge. It was built and completed in 2008 after the original bridge had collapsed in 2007. So first of all, I want you to appreciate the speed of construction of that new bridge. It was quite something, but the disaster itself was very bad. There was actually 13 people who perished. There was 145 injuries. And this happened in 2007 during rush hour, where the steel bridge that was there collapsed. So they had to quickly put up a new bridge. And not only did they want to put up a new bridge, they wanted to use the latest technologies to make an example, to actually as a memorial and as an example of how bridges should be built. They used high performing concrete. They used a lot of precast and some cast in place, but also used embedded sensors. So as they built these with a mix of, the piers were cast in place, but these box girders here were precast. As they built these, they embedded some sensors and attached some sensors onto the concrete, where we ended up having over 500 sensors. They called it smart bridge sensors throughout the bridge that are being monitored by the nearby University of Minnesota. And so the sensors on this bridge, they're attached to various points and embedded in certain points. Like you can see here, this is actually attached to the reinforcing as an example. And what they do is they actually measure and monitor movement of the bridge, vibration frequencies, creep, any potential for cracking. It even helps activate de-icing measures on the bridge, but it all helps a team monitor the strength, health of the bridge, right, as it goes through, and then they can detect if, for example, there's corrosion, or if there's, all of a sudden there's excessive vibration in one part of the bridge, and that can help dictate what kind of maintenance we're going to do for it. So pretty amazing stuff. Here are some examples of some of the gauges and sensors that were used. And by the way, at the end of this presentation, I'll have a list of references to all these projects that I'm talking about and things like that. So I would recommend that you read up on this particular bridge. It's very interesting. So the sensors I want to start with talking about are concrete temperature monitoring sensors. Now this is, not something that's coming or evolving. Well, it's somewhat evolving. It still continues to evolve, but it's something that's here now that you can use. And we don't use it a whole lot in the precast industry, but I think there's definitely a place for it. And that enables, so what happens is you take these small sensors and embed them into the concrete. So obviously they're one-time use. You embed them into the concrete, and then they can be read with a device, even with a cell phone, as the concrete is poured around it and it continues to cure. And what it allows you to do is use a system called, like, for example, the maturity method. Now, I'm not sure if you're familiar with that, but maturity measures the strength development or the curing development of concrete based on the temperature, because if there's anything that is a true predictor of concrete strength development, it is temperature. Temperature is, if you can chart the temperature that goes along with the strength development, you can develop a graph like this that enables you to then take this maturity index factor here that you develop, and you can come down here and say, okay, today, right now I'm at this, so that corresponds with 5,000 psi. In the morning, I can check it, and it corresponds with 2,500 psi. So instead of having to break a cylinder every single time you want to strip a structure or you want to do something, then you can actually use this, and it's very, very reliable to accurately gauge what the strength of the concrete is without having to always do cylinders. And they do this a lot in pavement, cast in place pavement, things like that. But I know there's some in the precast industry that have used the maturity method. I don't know if any of you have or are. I'd be interested in knowing if you do, but it would be an interesting thing to try out. These sensors and these little gauges are very inexpensive. And like I said, the technology is continuously evolving. Where you needed special equipment to be able to read it, you used to have wires that were sticking out that you had to connect to. Now you can do this wirelessly. And it's a great way, like I said, to monitor curing and strength gain. So like I said, you can use your handheld device and it will get a signal from these sensors, and you can use it for maturity method. Now they use this also for other means. They will use it for continued strength development beyond just the initial cure in the field, just to continue measuring what the long-term strength development is. Another type of embedded technology are RFID tags, and also along with what I just showed you for maturity method testing or strength monitoring, this is a technology that is here. It's been here for a little while. And I know a lot of our members use a tag that you can glue or apply to the surface of the concrete with a code that you can scan for inventory purposes and also to just track the structure. This is the same thing, but it's embedded into the concrete. This example here that we see here is embedded on the surface, so that somebody can come along using a piece of equipment, scan it, and then be able to track that structure throughout its manufacturing, when it gets in the yard, when it gets loaded, track its transportation to the site. And then once it's installed, then the user, the end user, whether it's the DOT or a private entity, can continue to use it later on if, let's say, there are issues down the road or they're having to rebuild a section. they can still scan that information and get when it was made. It could also store information like what water cement ratio was it, what was the mix design, what, just information about it that can help with forensic analysis in case something were to happen, but also just to help sort of track the history of how this was built. If it was something that was very, very durable, then they can look back and go, whatever they did, we want to do, right? So it's actually a very interesting technology. And now these tags, some of them can be embedded into the concrete. They don't have to be right at the surface, because one of the challenges with this is that it can get damaged during shipping and installation as opposed to the labels. But some of them can be embedded just below the surface where you can still scan it and still get the information, but it's less danger of damaging it. So I don't know if any of you are using RFID tags. I'd be interested to know if you are and what your experience has been with using them. But a great way to measure, to do quality control, tracking, but also inventory control. They also use RFID tags to monitor corrosion and strain, because what happens is they'll put these tags in the concrete, they'll join them with a wire, and they'll have it in such a way that if that wire is stretched and broken, then the RFID, that'll trigger a signal. So that's how they identify if there's been corrosion or if there's been excessive strain in the structure. So it's also used for those purposes, basically strength health monitoring, or SHM as they call in the industry. All right, what about smart concrete, right? We have smartphones, we have smart appliances, we have smart TVs. Can we have smart concrete? This is a structure that was actually 3D printed. So that's kind of a segue maybe to our next section, one of our next sections, but also it's been embedded with these fibers that enable it to be activated by touch. So if you touch the concrete, it'll turn these lights on and turn them off. So what that's going to lead to in terms of technology, I'm not sure, but for right now, it's pretty cool. So that's what I'm showing you. Now, who's this woman? This is Deborah Chung. She's professor of mechanical and aerospace engineering at University of Buffalo, New York. I just love her because she has done some amazing things just recently. And when I say recently, like within the last month, she was ranked the 14th among 177,931 material researchers in the world, based on the Stanford University study in 2020. That's not too bad. I'd really like to see what the other 13 are, but so nearly 2 decades ago, and then we had an article on this in our Precast Inc. She created a smart concrete by adding carbon fiber admixtures to a standard concrete mix. And what the carbon fibers in the concrete, what they do is they measure, it's basically like, it conducts electricity. So it'll alter the conductivity and resistivity values when the concrete is deformed or when it's damaged. So it can tell you when something has happened or when it has excessive strain. So it's pretty amazing just for that, but just all the other uses that can be done and have been done using carbon fiber embedded in concrete. You can put it on roadways to activate or use to get rid of ice and snow on the roadways. You can use the conductivity in the piece can help provide a shielding of the a shielding for like sensitive computer equipment. Some of you make underground infrastructure like utility vaults or even above ground that have sensitive equipment inside that need to be shielded. So this can be used as also for shielding, for protection. It can be used for weight monitoring, which I was wondering, what is that, a scale? But it can actually be used to detect if somebody's walking. So if you had a sidewalk outside of your building, it can detect if somebody is walking on that sidewalk. So it just detects changes in weight, which can be used for security purposes. It can also be used and has been used to monitor occupancy in a building. So if the building has a maximum occupancy, it'll weigh up that amount of people that's in there. And if you get over that amount, I don't know how it lets you know. How embarrassing it would be for me to walk into a place and then go, oh, sorry, you're over capacity. I don't know how it does it. Big alarm goes off. But just the ability to do that weight monitoring also allows it to gauge the structure, how healthy it is, the deflections and things like that, to warn in advance of any issues. And on top of all that, it can actually improve ductility, strength, and modulus, particularly when it's put under flexure, just because it's a fiber, right? It's a carbon fiber. So the normal, what the advantages of using fibers are. It also acts in that capacity, plus everything else we talked about. So I thought that was very interesting stuff. And talking about smart concrete, add to that smart paving slabs, that can be used and are used to help power electric vehicles, to help with what do you call that? Vehicles with no people in it. Not no people, no driverless vehicle. You know what I'm talking about. And also these sensors are able to, it's almost like, I like this analogy. It's like the paving slab, and these are precast paving slab examples shown here. It's like these paving slabs are like the face of your smartphone, the glass face of your smartphone, where it detects obviously where you're touching and how hard you're touching and how long you're touching. It's sort of that technology, but with a paving slab. So it can tell how fast the vehicle went over it. It can tell where the positioning of the tires were, this kind of stuff. So it feeds back the data on traffic, things like that, but can also do other things like provide live traffic updates. If you have an accident, it could immediately notify your emergency services because it detects the accident. It can provide Wi-Fi. It can actually, you're driving down along the highway and you have this continually high broadband service just under your wheels. So it's kind of an interesting prospect that fits right in with another evolving technology that we've been working on. Our members have for a few years, and that's precast concrete paving slabs. So just another use or another advantage to using that kind of system. Here's an installation. I think this was in Chicago. I'm not sure, where they were using this autonomous. Thank you. I knew there was a word. It was some kind of weird word. I was going to say anonymous, but that doesn't make sense. All right. What are potential impacts on the precast industry with embedded technology? Well, enhanced quality control. Imagine being able to track your products and track it through the quality control process, obviously inventory control as well, but to use it especially in the maturity method. If that's something that you're interested in learning more about, I would strongly recommend it. And also by tracking. Structural health monitoring of the structure while it's in service. And it's also an added value for owners and end users based on what technology is in there, and it allows them to do, like power up these vehicles. A lot of the buses nowadays are electric buses. So they've built, even if the whole roadway doesn't have this, some sections where the buses pull up have a charging, so they can charge the bus while the bus is just sitting on it. Okay, moving on. Whew, I'm tired already, but it's exciting. There's just so much to talk about. All right, polymers. So polymers is a word that I'm sure you've heard, and it's all around us. Like plastic bottles have polymers. The clothes you're wearing have polymers. There's things in your body. DNA is a polymer. So polymers by itself, it can be organic, it can be natural, and it can be man-made. Polymer, which is a Greek word for many things, and monomer is one thing. So polymers is basically a chain of monomers, right? It's or monomers. I don't know. Monomer sounds better. I don't know about monomers. So as you polymerize these monomers together, you make a polymer. So I like to think of it like a chain. If you're holding a chain, then the whole chain is a polymer, but each link is a monomer. Okay. So there's various things. Starch, for example, starch in your food, that is a polymer, and the monomer is glucose. So glucose chained together makes a starch. So it's used in a lot of different things: clothing, medical, consumer goods, and also concrete. I bet you didn't see that coming. All right, but first I want to make this differentiation between polymer concrete and polymer in concrete. The S, by the way, should be down here. Never point out your mistakes, but that's just for next time. Okay, polymer concrete. Now, polymer concrete, which you may have heard of, and for some of you may raise the hair on the back of your neck, because it's a composite material that has aggregates, but it has a polymer binder. So it's not a cementitious material. And for some of us, for the products that we make, it may be like an alternative material that is in your market, right? It's something you're competing against. Of course, precast concrete is far superior, but it's a product that is out there. So that's polymer concrete. I hate the fact that it's called concrete because it's not real. To me, it's not really a concrete, right? It's just like if you look at the Freddy's menu, if you go to Freddy's Steak Burgers, they have concretes. Well, that's not they don't put Portland cement in your chocolate concrete, I guarantee you. So it's about as concrete as that is, but they call it concrete. But that's not what we're going to talk about today, because we're going to talk about how polymers can be used in concrete, all right? Polymers in concrete, like for example, polymer impregnated concrete and polymer modified concrete. So polymer impregnated concrete, first of all, is when hydrated Portland cement that has been impregnated with this monomer. So when a daddy concrete meets a mommy concrete. No, I'm just kidding. So impregnation, by the way, impregnation, which is defined in ACI, American Concrete Industries, as the act of saturating the voids in hardened concrete with a monomer or a resin. So how this works, and this is kind of quite an involved process, but it could be done. It's actually very applicable more to precast, I think, than it would be to cast in place. So there's a few stages with it. First of all, you have a piece of concrete and you want to impregnate it with polymers. And what you can do is you can do it partially, where it's a partially impregnated, which is usually like 85% or less of the voids are filled with this polymer, or you can that's a full impregnation. A partial impregnation would be less than that. And that's where maybe you would just impregnate the very top surface of a concrete, because that's what's going to be exposed to a very harsh environment, right? So you take this concrete, first of all, you have to dry it. You have to dry it to this incredibly high temperature, to the point where, because you're trying to dry out all the water that's in the voids, which is kind of a challenge to do. So that would be one of the first challenges, is to dry out those voids. And the temperatures that you use, you'd have to be careful to not use temperatures that are so hot that you're melting like the chairs that you have in the concrete that are actually holding up the reinforcing. Things like that you'd have to keep in mind, but you're heating up the concrete to get the water out. And then once you have the water out, then you impregnate it with these monomers, and whether it's a full or partial, by basically, you can do it through liquid or gas. Liquid is the most often used, but you can dip this piece in the monomer that's in a liquid. So very similar, some of you do pipe or forms, where you take the forms and you dip them in the form release in a dip tank. It would be kind of like that. You take the concrete piece, dip it in a dip tank, and either partially or fully, to get the monomers to soak into these voids. Once you do that, then you have to do the polymerization, which is done through a couple of different means, which creates, it's either, there's partial, let's see, there's a couple of different means. Thermal catalytic and promoted catalytic. I'm not going to get into the details of that, but that's another stage that has to be done using one of these materials. It's usually methyl methacrylate is very often used, or styrene, or other products. But what ends up doing after you do the polymerization is you fill up those voids with this polymer, and it provides for a very strong but also very, very durable concrete. Now, another thing that can be done with the polymers is polymer modified. Now, this is a little easier to do than the polymer impregnated. The polymer modified cement concrete, it's also sometimes called PPCC, polymer Portland cement concrete, or latex modified concrete, which the latex modified concrete is used more for repair and toppings, but it's basically just mixing polymers in the concrete. You would be mixing it just like you would be mixing an admixture or mixing a fiber, with however the polymer is carried, okay? And that can also lead to a stronger concrete, a more acid resistant, a much more chemically resistant concrete by using these polymers to help fill those voids. Again, always talking about filling those voids and making it stronger and more durable that way. Another thing that polymers are used for is internal curing. Now, you might have heard of internal curing through using lightweight aggregates, where the aggregates are soaked with water and then they release water from within the matrix. Because if you look here, you know, if we do normal curing where we apply moisture or retain moisture to the external of the structure, or external curing, then really the water penetration is kind of limited to wherever the surface is. And then in the inside, you can have desiccation caused by water leaving the area, whereas internal curing provides moisture. It keeps the moisture in the concrete, so you don't have that desiccation. And when you don't have that desiccation, what happens? You don't have that shrinkage, right? You don't have that inherent autogenous shrinkage that comes with having, you know, typical concrete because of the loss of moisture in the concrete. So instead of using lightweight aggregates, they've made polymers, super absorbent polymers, or SAPs, as they're often called. Same kind of things that maybe you'd see in diapers and things like that. You know, you add them to water and they immediately soak up like a whole lot of water and they expand. Well, they can be added to concrete, and somehow the technology allows the polymer to know when to hold the water and when to release the water, so that it is available for moisture while it's curing. And these super absorbent polymers can really help with strength development and a lot of other properties as well. This is also another form of biomimicry in a way, because it's mimicking the it just left my head, a type of plant that works very much in the same way, where it's super absorbent and releases water when it's needed. Okay, and then also self-healing concrete using polymers. Imagine having concrete that could just heal itself if it needed to heal itself. And so this is a diagram of concrete crack that heals itself after a certain amount of time. You can see there as it heals itself. And a lot of these technologies use like a calcium carbonate or some kind of material that is secreted or released whenever there is damage to the concrete. And that can be done either through encapsulated polymers. So when the encapsulation is broken, it releases a material that fills the crack. There's a technology that uses a bacteria, an actual bacteria that is embedded in a super absorptive polymer. And when it's released, it releases material to fill in the cracks. And then others use calcium carbonate producing bacteria that do the same thing. So that's basically the essence of self-healing concrete. And a lot of these technologies use polymers. So polymers can really be helpful. It's not something we use a lot of in concrete. I know some manufacturers of precast concrete do manufacture some polymer concrete, maybe smaller structures, as part of their inventory. And some may use or have tried using polymers. There again, I'd be interested in knowing if you or if you've known of somebody that has tried to use polymers in their concrete to see how that works. But it can give you enhanced durability and overall strength increase and lower permeability, and also extended service life, especially in aggressive environment. Whew, 10 minutes. Okay. Carbon capture, I'm going to go through real quick. Now, carbon, CO2, you know the term CO2, right? So CO2 in the atmosphere, what leads to the heavy CO2 in the atmosphere? A lot of things, auto emissions, but also industrial plants, large plants that release a lot of carbon dioxide and ends up in the atmosphere as pollutants. One thing that also does that is the cement industry, right? The cement industry releases a lot of CO2 by virtue of the type of fuel that it burns in order to create the clinker, but also through the calcination process of the limestone. So what can we do? Well, they've developed a technology where you can literally, now try to get your head around this, they can literally go out and capture these emissions, capture the carbon, okay, out of these facilities, and then collect that, purify it, and change it into a liquid. And what a lot of these technologies have done in the past is looked at injecting it deep under the earth somewhere, where they just drive it down into like a really deep well or something and they cap it off. That just sounds like the beginning of some kind of disaster movie to me, but apparently it's something that's been done, and it just like sequesters it somewhere else. So it's a way to clean up the air. But recently, or fairly recently, there's been some companies that have started and that have been studying how to do that with concrete, adding it to the concrete mix to not only sequester that CO2, but also possibly enhance the quality of the concrete. So what happens is that CO2, once it's mixed, this product, once it's mixed into the concrete, it mineralizes through a reaction. It actually mineralizes into calcium carbonate, which we've talked about calcium carbonate a couple times, and creates this calcium carbonate, which can end up enhancing the strength of the concrete. It's not been used in precast all that much, but they've used it a lot in cast in place. They've used it in masonry applications, and in some cases can actually enhance strength. But at the very least, it helps severely lower the amount of CO2 that is inherent to your product. Like in this case, they claim 25 to 40 pounds of CO2 saved per cubic yard. That's significant. That's a significant drop in your footprint. Now, this is a technology that, while it's very new, it's something that has already hit the streets. Like I said, there's a lot of concrete companies using it. Recently, we've seen some legislation introduced in various states to incentivize the use of carbon capture. So it's definitely something that you should look into and see if there's some interest there, and even trying it. If you're interested, let me know and I can connect you to the right people. But it's something that we're going to see and hear a lot more of. So in terms of the impacts, well, yeah, potential higher strength, potential better quality concrete, but the biggest impact is really the lower embodied carbon. It would just severely help cut down that amount of embodied carbon that we already have due to the use of Portland cement. Okay, and finally, last but not least, is 3D printing. We're looking at a 3D printed building here. This is being claimed as the largest 3D printed building ever built. It's about 30 feet high with it's about 6,800 square feet inside. And it's this company in Dubai that built it, this 2-story building, just using 3D printed. Well, they used a combination of 3D printing and precast. Here's the manufacturing of it. So you see this robot here in the lower left that places the concrete where it's placed. So it's moved, and then it places the concrete automatically as per the software that it works off of. You can see that it's not filling up that wall, but it's just building this honeycomb. So it's using less material. Here's a closer look at it. Now, already, if you look at that and you think, oh, okay, that's pretty cool, but what are the challenges here, right? We'll get into that here in just a little bit. So when we talk 3D printing, there's a few different things that I want to talk about with the very little time I have left. Models, formwork, and concrete. The first one on models, and I've got an article that's going to be coming out in Precast Inc. on this topic, but I've talked to, and I've seen that more and more companies have actually purchased a 3D printer, and they're very affordable now and easier to use than they've ever been, to print small replicas of, like, this is a box culvert section. Here's a tank, a screening tank for a stormwater system. That's fairly complicated. And if you were producing that in the plant, wouldn't it be nice to have a model of it, of how you were going to separate it, so that you can figure out how you're going to pour it, how you're going to lift it, how you're going to get it on a truck, how's the contractor going to put it in the ground. It's easier to envision if you can hold it in your hands and manipulate it, than looking at it on paper. Other advantages have been that people have used this not only to help with production, but they've used it to help with marketing, with sales. They send their salesmen out with these pieces. Some contractors have been asking, hey, can we have a 3D printout of our box culvert? So it's been kind of an added benefit. And like I said, they've become very, very affordable. There's different types. There's some that basically print out of a liquid from bottom up, and some print, well, this print bottom up and some print from top down. This is a bottom up printer. A lot of them, very, very good printers you can buy for under $1,000. Very affordable. Some closer to $500 where you can buy them. And basically it just, there's a lot of software that's available now. You can use CAD and CAD 3D if you have it. But there's other software out there where you can enter the information, and then from there, there's software that comes with the printer that's able to render that into an actual printed piece. And you can use it in production, sales, installation. If you're teaching courses or you're going out to schools and universities using it for outreach, I think it's a great idea, and I think a lot of you should definitely look into that. Now, if we look at a slightly larger scale, this is the Domino Sugar Building in Brooklyn, New York. 42-story commercial residential tower, and there's over 1,500 window openings, some as high as 12 feet. And they were going to need, the precaster was going to need more than 120 molds to make these different shapes, out of lumber, or, the different types of molds they were going to have to make. So they ended up talking to some folks at the Oak Ridge National Laboratory because they had a system of 3D printing, and they had a system called BAM, which is big area additive manufacturing. By the way, if you ever hear the term additive manufacturing, that's a form of 3D printing. It's the term they use when you're talking about larger scale. Okay, instead of saying 3D printing, they say additive manufacturing. So same thing. But they partnered with ORNL, and they developed this system to print these molds, and they printed those molds using some kind of a carbon fiber reinforced butadiene styrene system, like a thermoplastic, and they printed about 35 molds that they were able to use for 200 casts. And there's the printing of the mold, so it definitely saved a lot of time over having to build this with lumber. And here's the resulting structures that were used on the building. So it can be used to create blockouts. I know a few years ago at the Precast show, there was a company there that was exhibiting on this very topic. I don't think they were at the last couple of Precast shows, but I think they were there in 2019. They also use this technology for form liners. A lot of the form liner companies, you send them the pattern that you want to do, and they'll enter it and print out the either print out the form liner, or they'll print out the master mold in order with what to print the form liners on, or create the form liners on. So definitely something on a slightly larger scale that can be done. And then when we're looking at much larger scale of actually printing concrete, well, it's being done, as you saw with the building I showed you earlier. And here's an example where they're printing what I assume to be some round, like a manhole or some round structure. But if you look at it, you can already see, well, as far as the finish, it's not ideal. If this showed up on your job site, you probably have some questions. Here's a building. Once again, the finish of it still has some challenges, but it's a very, very interesting and developing technology that'll continue to develop, and will have an impact, I really believe, on our industry. And hopefully it's a positive impact. And I really do believe that. Some people are worried that it's going to end up being a competitor, but I think we'll be able to find some applications for it in the plant. But the challenges for right now are like the concrete fresh properties. You actually have to make a concrete that is flowable enough to come out of a nozzle, but then strong enough to retain its edge and support subsequent layers. So that can be pretty challenging. They're having a hard time coming up with a system that can handle the larger aggregates that we use. So right now it's being limited to a lot of the smaller aggregates. Reinforcing. So there's not a system out there that I'm aware of, at least, that adequately places reinforcing in these walls. So they have to be placed by hand or some other method. So that building in Dubai, I don't know if there's reinforcing in there, but if there's not, it's not a building I'd want to live in. You know, it's nice to visit, but I'm not sure what the strength of those walls would be. So placing the reinforcing, I know there's machines that will lay out some wire as it goes along, but it's not substantial enough to meet the requirements of ACI 318 and other requirements for reinforcing. But once again, that's being worked on. The speed of the printing, you know, it's getting faster and faster, but it can still take a while to print one of these larger structures. And as you saw, the finishes where it looks like corduroy on the outside, you know, if you got to come along behind it and smooth that all out, there's still a process involved there. So it's a technology that is evolving enough that ACI has a committee that's devoted to this, ACI 564, 3D printing with cementitious materials. I've been going to their meetings, I've been monitoring what they're doing, and here at NPCA, we've been monitoring 3D printing as a whole. We've been talking to folks over at Oak Ridge. We hope to go visit them soon whenever we can, and we'll continue to monitor this, any advances to see where it could be heading in terms of impacts on our industry. So 3D printing, really, the 3D modeling, that's already here, that's here now, and I love that. That's a great idea. Definitely has some benefits in terms of being able to address some production, R&D, all kinds of stuff. It could be an opportunity to address workforce challenges through automation. If we can automate some of our processes in the plant, it could help dedicate our existing workforce to other things that we need. I know a lot of us are having a challenge just to get the workforce we need, so anything we can do to cut down on that need might be a big help. And further advances could actually prove very beneficial to precast manufacturing. But we'll see, we'll continue to monitor, we'll continue to let you know. I have run out of time, so I'm not really going to be able to go through these in a lot of detail, but there's a lot of work on alternative binders to Portland cement, aggregates, especially as it relates to using recycled aggregates in concrete, which would also help quite a bit on the sustainability of concrete. Reinforcing, just different types of reinforcing, different types of fiber reinforcing, still advancing. Admixtures, that's always been a very evolving part of our industry, and they're continuing to do so. And then the manufacturing equipment, you know, you've seen probes and things like that that measure your air content in the mixer, like all kinds of cool stuff that are coming out now. But that's continuing, you know, laser systems that lay out wall panels and all kinds of stuff that you see at these international shows that will eventually make it onto our market, will help make our manufacturing even more lean and more efficient. So it's exciting. It's an exciting industry to be in. Aren't you glad you're in it? And I'm glad you were here today. Thank you, Nadine, for mentioning Garden State Precast, and they helped me quite a bit on my article. They use 3D printing, 3D modeling. In case you have any questions specific to it, give them a call. I'm sure they'd be happy to talk to you about it. So as a recap, precast concrete manufacturing, always been on the leading edge, really, of concrete technology. Let me ask you this, who used SCC first? SCC used to be a new technology. And to many in the cast in place industry, it still is, because they're just now starting to use it. But precast concrete was an early adopter. So we have been always open to using new technologies early. Familiarizing ourselves with these evolving technologies will help you as owners and management to make informed decisions on what's going to work best for you. Because like I say, you guys all have a lab. You all have a lab, not just a plant. You all have a lab that you can do. You can conduct experiments with your concrete. You can try out some of these technologies, and it's always going to give you an edge in being able to stand out from your competitors, stand out from the others when you're able to use and offer that technology to your customers and to keep your workforce safe. Whew. All right, there's some references at the end, which I think are included in your handout. There were a couple extra slides that weren't in the handout. So if there were some slides that weren't in your handout that you really want, I'm happy to send it out again if you let me know. That's the end of my presentation. I'm sorry I went over a little bit, but that is how I operate, as you know. But it's only 5 minutes. if you have any questions.
Claude, we actually do have a couple of questions.
What?
Are there standards for polymer concrete?
Standards for polymer concrete. Yes. Now, I'm not sure. I'm sure there are within ASTM, and I don't know those right offhand, but in ACI, there's actually an ACI document on the use of polymers in concrete. And I don't know that right off the top of my head. I don't know if I showed that while I was talking about it, but I'm going to rifle through some paperwork I have here and find it for you while you go to the second question.
The second question is, does 3D printed concrete use reinforcement?
Well, yeah, I talked about that a little bit, but the 3D printed. So the question was about the use of reinforcing in Oh, thank you. ACI 548. ACI 548. It has a guide, and it's actually in the references. I should have just pointed to that. It's actually in the references. There it is. Yeah, right here, 548. If you click that link, it'll take you to it, but there's a guide on the use of polymers. Okay. In terms of reinforcing, yeah, the challenge is it's been very difficult to place reinforcing in 3D printed concrete. So what I've seen a couple of, like I said, where when they add a layer, so they put a layer, it's almost like they're squeezing out toothpaste, right? And they go along, they add a layer of concrete or a mortar of some sort, and then they kind of lay in this line, this wire along the top of it afterwards, and it helps bond the next subsequent bead onto that one. You know what I'm saying? So it's more for the bond between layers than it is for actual, load resistance. The only way that I could see where they could address it now is if you already had a cage built, so you have a cage of reinforcing and you have the cage sitting there, and then the 3D printer somehow, like it has a machine on this side, a machine on this side, and it oozes the concrete out from both sides, brings it together and moves back. You know what I'm saying? I don't know if I can explain that very well, but would it happen to print the concrete around the reinforcing and through it? But you'd still have to obviously construct the reinforcing, place it. The only thing you'd be saving is a form, right? You wouldn't have to use, theoretically, you wouldn't have to use formwork. But how much time would that save once you add in like how you'd have to finish it? There's definitely a ways to go. And this could be something that in 20 years we look back at and go, remember that 3D printing phase we went through? But I don't know. There's a lot of resources being put in by the federal highway, by a lot of government entities, which by itself doesn't mean that it's a viable thing. But there seems to be a lot of scientific focus on it that would tend to make me believe that it's going to go somewhere. We're going to see something we hadn't even thought of. And but I don't know. When you think about it, precast concrete almost in a way is 3D printing. We were 3D printing before 3D printing was cool because, our little nozzle is the bucket that is moved around by hand, but, the bucket moves around, places the concrete, it's within formwork, but, we're already kind of doing that. Maybe there will be some evolving technologies that will help with automated guidance system of that bucket and how it's placed where, once again, I could see that with robotics. Moving in that direction. That's already done with some precast products. So I could see that evolving faster than just doing 3D printed concrete. But anyway.
One final question.
One final question.
Is self-healing concrete being used in real applications that we know of, or is it still in R&D at the university or research level?
So is self-healing concrete being used, or is it still in R&D? Self-healing concrete is being used. Now, I can't give you a specific case study, but it is being used in certain applications. I know that it was being used in some kind of a topping material on a bridge here in the United States. If I find those case studies, I'd be happy to send it to the attendees. But yeah, it's definitely being used. I wouldn't say it's in widespread use, but yeah, it's found the market as usual more in Europe than here right now. But is that it? All right. Well, thanks everybody. Appreciate your questions, and I'll turn it back over to Kathy.